Okay, let's get started. So actually we have finished the software security part. So starting from today, we will spend 3 modules on something a little bit lower than the software layer. We're talking about the microarchitecture layer. However, the way we exploit it, we are still using instruction set. But the vulnerability itself is not really at the instruction set level. It's not really at the software level. It's in the CPU. So in those 3 sessions, we will first talk about what is cache side-channel attack in general. We will touch famous or infamous meltdown and spectrum. How many of you heard of that before? They were kind of big 2-3 years ago, maybe 3-4 years ago. So basically, CPUs that were manufactured in the last decades or 2 were found vulnerable to those kind of attacks. So the vulnerability has been there for many, many years, but no one knew that before. So in the last 40 years, the speed gap between CPU and the main memory is getting bigger and bigger. The ideal memory or storage system should be super fast, which means as fast as a CPU, super large and super affordable. Unfortunately, in reality, we don't have such memory or storage system. So fast storage systems usually are very expensive and very small. For example, in CPU, the register itself, that's a very fast storage. The register usually is made by SRAM, very fast, however, very small, right? The register we're talking about usually are several 32 bytes, 4 bytes, 8 bytes. Those are very small compared to your main memory, several gigabyte compared to your hard disk storage or SSD. On the other hand, those very affordable ones, like hard disk, they are very slow. So the strategy to make your software and hardware system to run faster, to handle this problem, is to put faster memories closer to the CPU. And at the same time, we try to keep the frequently used data or code in the faster storage. So we do not have to resort to those slow storage very often. And that strategy, basically, we use something called a cache. And the cache could be at many different levels. You have a browser. Your browser visits different websites, and you visit a website. Your browser probably will save a cache, and that is also a cache. That's a file in your local file system. So accessing that file is faster than accessing the website remotely. So that is cache. But here in this class, we talk about CPU cache. So CPU cache is a very small amount of fast and also expensive memory. It is actually usually made the same material as your CPU registers. It's a SRAM, static RAM. So the cache is between the register and your main memory. So usually we use DRAM as main memory for our laptop, desktop, phones. We use DRAM. For some low-end devices, we do not need a huge DRAM, so we only have a SRAM. SRAM is fast but very small. So in cache, we keep a copy of the most frequently used data from the main memory. So the idea is, when we request for some data, we don't have to go to the main memory. We only need to go to the cache. Cache is part of the CPU, okay? So modern CPUs, there are several levels of cache. At different levels, we have different policy, and their sizes are also a little bit different. our modern server laptop CPUs, Intel-based, usually have 3 layers of cache. And the ARM-based CPUs, like the phone we are using, usually 2 levels of cache. And they are all part of the CPU, okay? So here I have some very old data, like 10 years ago. So this is a speed difference from accessing data from cache or other places. So that if the CPU access data to retrieve the data from cache, which is a static RAM, it takes 0.5 to 2.5 nanoseconds. If the CPU, because the cache is part of the CPU, super fast. If the CPU takes data from the main memory, the DRAM, which is not part of the CPU, it's another module on the motherboard. You have to talk to get the data through a bus. That will take 50 to 70 nanoseconds. If there is another secondary storage like a flash or even hard disk, then it will be much slower. However, those devices are huge and cheaper. So we talk about 2 important concepts here, very easy to understand. One is called cache hit, another is called cache miss. So we call it a cache hit if the cache contains the data the CPU is looking for. So cache hit is a good thing. It means the CPU only needs to go to the cache to retrieve the data. Doesn't need to go to the another layer of memory like the DRAM. And a cache miss means the cache doesn't have the request data, but the CPU still needs the data. So CPU will go to the DRAM to retrieve the data. So cache hit means the CPU can get the data very fast. Cache miss means the CPU will get the data in a very slow way. And as I just explained, usually we have hierarchies for cache. L1 cache is closer to the CPU. Physically, it's closer to the CPU computing unit, as I will show you some image later. Physically closer, so it's even faster. Even if it's the same material, it can be even faster. And the L1 cache usually is divided into a data cache and the code cache. So data is stored in the data cache, code is stored in the code cache. So for a lot of architectures, we have this. Then L2, L3, level 2, level 3 caches are usually unified. So we store data and code there. So here I have a very old CPU footprint. I'm not sure what CPU this is, but let's see what we can find here. We have a floating point unit to do floating point calculations. So this looks like a RISC CPU because there is a node and the store modules, and there are execution modules, a little bit bus unit, fetch, scan, alignment, micro code. Then we have a memory controller. So there could be the MMU on the CPU. So you can say this CPU is this big. This is like 65 or 70% of the CPU, the area is used for cache. Here we have the data cache, and then here we have the instruction cache. So that is the L1 cache. The L1 cache is divided in data and instruction. Then we have a huge area for the L2 cache. This is the old CPU. It's only just 1 megabyte. Okay. So you can see maybe 65, 70% of the CPU area is actually used for cache. So this is a very important physical module in the CPU. So here's another one. This is also an old CPU. This is a 2003 Intel Pentium 4. So this is kind of like almost 20 years ago. And the same thing. So here we have L2 cache. Here we have also L2 cache. I don't know where is L1 cache somewhere, but there are some other cache modules on this CPU as well. Let me find, for example, here. Instruction TLB, the cache. That is, so you guys took operating system class. So you know operating system, we use MMU to translate the virtual address to physical address. And the translation is very slow because the translation is based on a table. That table itself is big. So that table itself cannot be stored in any special hardware. The table itself stores in the main memory. So to the translation, you have to walk through the table. You have to do several queries to the main memory, which is very slow. That's why there is a special cache for that. It's called the lookup table cache, TLB cache. So when the CPU does a translation from virtual address to physical address, it will remember the translation. The next time it will just get the translation from the cache, the TLB cache, not always do the work, do the table work, which is very slow. This is probably a newer CPU, and you can say this is a multi-core CPU. We have 8 cores here. This is probably Intel CPU, and the last part is the memory controller, the MMU. In the middle, we have the L3 cache. So this is a level 3 cache. What interesting about this is you can say all eight cores, they can access L3 cache. All of them, they can access L3 cache. However, each core, they have, from here, we don't see the labels for L1 and L2 cache. That's because they are inside each core. So each core has its own L1 and L2 cache. They do not share L1 and L2 cache. But some of the CPUs, they actually have protocols, hardware protocols, to retrieve other cores L2 and L1 cache. They can still retrieve each other's L1 and L2 cache. There are a lot of protocols to do that. Okay, so you see, cache is super important. It's take most of the space of the CPU, almost. Then we are talking about some more concepts in cache, so we can understand how it works. The first concept is cache line or cache block. So this is a minimum unit of information that can be either present or not present in a cache. So when we talk about the main memory, we think about the medium unit is how big? When you write a C code, you access memory, what is the minimum unit you can access? Yeah, you can do 1 byte. Actually, you can even do 1 bit, right? That's a 1 byte or 1 bit. That's the smallest. But for cache, it's different. So if you move something to cache, you do not move 1 bit into cache. You do not move 1 byte into cache. You move a cache line into the cache. And for modern Intel and ARM CPUs, that is 64 bytes. But you do not explicitly move things into cache. There is no instructions for you to do that. Everything is transparent to the software developers, automatically done at the microarchitecture level. But remember, the system we talk about, the minimum unit, a cache line is 64 bytes. Then the cache policy we are using now for all our CPUs, the policy we are using is called the n-way set associative cache, which means any given block in the main memory, the DRAM, may be cached in any of the n, which is the n-way, n cache lines in one cache set. Okay, there are so many concepts there. how many ways, cache set, those kind of things. So we're going to discuss them one by one. What do they mean? So let's start with a 32-bit address. Let's say this is a virtual address, 32-bit in a 32-bit machine. And it starts from bit 0 to bit 31. That's an address, virtual address. So if the data at that address needs to be stored into the cache, so where do we store it? That's a question we want to answer here. So let's say we assume our cache. So you see the address space is 32 bits, which means it's 4 GB of the whole memory. But our cache, let's say, is only 32 kilobytes. We only have 32 kilobytes of cache, and we want to store huge memory address data into that place, which means a lot of different addresses, they will go to the same addresses in the cache, right? However, for each address in the main memory, there are multiple choices, and that multiple choice is n. So in this case, let's say we have a 4-way cache, which means there are 4 possible addresses in the cache we can go to. And because each cache line is 64 bytes, which means the last 6 bits, the last 6 bits of your virtual address will be used as the offset. So this one will not determine which cache line you go. It only determines in each cache line what is your offset. Okay. Then in the middle, here we have something called the set. This is the concept of the cache set. And at the beginning, we have something, the highest bits are called the tag. The middle bits are called the set. Set is not stored with the data. The tag is. So use this equation, we can compute how many sets we need for this cache. The cache size in total is 32 kilobytes, which is 32 times 1024. The number of ways, we have 4 ways. Each line is 64. So if we use the cache line divided by number of ways times line size, we get the number of sets we need for in this cache design. And in this case, we have 128 sets available, which means we're going to have the cache is actually divided in something like this. 4 ways, you can think there are 4 bags of cache. Okay, 4 bags of cache. All the things together, we're adding them together, we have 32 kilobytes, which means each of this is actually 8 kilobytes. Then for each of this bag, we call it a way. There are 4 ways. Then each way, we have the number of sets. Based on our calculation just now, we will have 128 sets. Okay, so they are labeled from 0 to 127. So let's say we have a data at some address. That data, 64 bytes, can go to 4 different addresses in the cache. First, from its address, we can get the set. The middle, the bit 6 to bit 12, that is a set. So for the set, then we know it should go to, let's say, 0, 1, 2. Let's assume this data, the address, this address part is just 2. Those bits are 2. So this data will only go to the set number 2. However, it will go to either here, 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 or here. 4 possibilities. It can go to all those, any of those 4 cache addresses. And those 4 cache addresses, they are called a set. The row here, we call it a set. So data can go to either address of the same set. It can go to all of those. However, it will never be able to go to here because which set it goes to is determined by its own address. Okay. So what do we actually store here? Obviously, we will store the data. The data is 64 bytes. That is what we're going to store there. But we will also store some metadata. First of all, we need to know the data we stored in the cache, what is the original address, right? So to remember that, first what we need is the address is 32 bytes, 32 bits. Do we need to store the offset? We don't, because it's 64 bytes. We're storing 64 bytes of data. So we don't need to really store the offset. Do we need to store the set number? Also, we don't, because the set number is determined by where it is stored. If it is stored here, then the set number is 0. So that we can construct all these parts. However, the tag we need to store because there is no other where we can reconstruct the tag information. So tag, in this case, in this figure, it's 19 bits. So we're going to store that 19 bits of information with the data. The data itself is 64 bytes, okay? Then there are 2 more important tags. 1 bit information we need to store. Modern cache could be much more complicated than this, but I'm just telling you the most important ones. One is the D tag. It's called dirty. Another one is V, or valid. The dirty tag indicates what you have in the cache, whether what you have in the cache is consistent with what you have in the main memory. If you have a load instruction, you load something from, when you have a load instruction, your ultimate goal is to load data from memory to your register. That's your ultimate goal. But it will not directly do that. It will load the data from main memory to the cache and also to the register. Then if you do some computation on this address data later, the cached value could be changed. So technically, every time the value is changed, we should write it back to the main memory to make them consistent, right? But the memory write will be slow. What if you are going to do 3 operations and you are only going to use the memory, the data somewhere again later? So you don't have to write it back. You can save some write backs there. So in this case, how do you show that your data in the cache is not consistent with the data in the main memory? You set the dirty bit, which means it's dirty. It should be written back to the memory at some point. And the valid bit is easy to understand, just showing whether we are using this cache line. It's possible that we're not, most of those cache lines we're not using, okay? As you can see that each memory address in the main memory, the data there can be placed into multiple ways, and but it can only go to one cache set. On the other hand, the memory address is so huge, so the memory so different memory addresses, especially the ones with the, well, actually the ones with the same set numbers. We don't care about the tag number. We only care about the set. The memory addresses with the same set values, they will all go to the same memory. They will all go to the same cache set, right? They do not necessarily at one time go to the same cache line, but they will always go to the same cache set. That's for sure. Okay. So those addresses we call it congruent addresses. So those addresses, they compete for the cache lines within the same set. And we know that in each cache set, there are only limited numbers of cache lines. So basically, that's the N-way, the 4-way, 8-way, 16-way, whatever. Since there are only limited ones, which means if those cache sets, if one cache set is full, and we need to bring a lot of data here, then we have to replace what we already have in the cache set. We need to replace one more line. And there are many different policies to do that. I list several policies here. The first one is called the least recently used policy. In one cache set, we find out which cache line haven't been used for the longest time. Then when we bring new data, we replace that one. Okay, sounds reasonable. The problem is, this sounds a good way. However, you need an extra circuit to do this. Everything here we're talking about hardware. The second one, because for example, in this way, least recently used means you have to remember when was the last time each cache line was accessed by the CPU. If you do not remember that, you cannot find which one is least recently used, right? So you need to remember that. That's probably several bytes you need to remember there. The next one is first in, first out of FIFO. So first in, first out, technically, you still need to remember the order of everything, right? Yeah, you need the order of everything. Also, we have a least frequently used. For example, in the last 100 instructions, which cache line is least used? You also need to record those information. So I think most powerful CPUs, like Intel server CPUs, we are using either least recently used or least frequently used. They're more complicated. It's the policy itself is good, but it's also it requires extra circuit, so make the CPU more expensive. So for most ARM CPUs, especially low-end devices CPUs, if they have cache, they usually use just a random. So they don't care which one is least recently used. They don't care which one is least frequently used because they don't have the ability to record those information. If the cache is full, we need to bring a lot of data into the cache. We just randomly evict one from the cache. Okay, that's yeah. You don't need a clock here. So how do we generate the randomness? Well, here all the randomness is at a hardware level. So the question you ask, I imagine you are still thinking about the C code level, right? You're thinking you use the C library, C or SRAM, right? Those kind of things. So here we're talking about hardware. Maybe the hardware has a true random generator. We're just magically give you a random number. Yeah. Okay, now we have all the background we need. We are going to move to a text. We are going to talk about cache side channel attack, which has been a very useful attack vector in the last at least 15 years. And the advanced attacks like meltdown spectral, which is more than cache side channel attack, but they still rely on cache side channel attack. And all of them are side channel attack. Okay. Cache side channel attack basically utilize the time differences between a cache hit and a cache miss to infer whether specific code and data has been recently accessed. Because a cache hit will be super fast, the cache miss will be very slow. If we compare them, we can tell the difference. And because of that, we can guess. It's not always deterministic. Sometimes there are some randomness, but most cases we can guess with very high possibility that which data has been recently accessed. We're going to say some examples today. Let's say here I'm actually using ARM instruction. So let me explain a little bit this instruction. Here we have two registers, R0 and R1. Okay, this is ARM. So we're not using EAX, EBX. The names of register are different. We have R0, R1. R0 already has a value 3000 hex. R1 doesn't really matter what the value is. Then we have the main memory, which is a DRAM. At DRAM, we have those addresses. The example here, the example I'm giving is not very accurate because technically it should be those addresses should be at least the size of cache line. But I'm just trying to give you a high level idea. Let's say at the address to FFC, we have the value 0, and memory 3000, we have value 1. The 3004, we have value 2. And the instruction we are going to execute is LDR, which is load. This is basically the move instruction in ARM. It's load. We are loading from the memory address R0 to register R1. Okay. So this is just a move instruction, like a move EAX, bracket EBX, something like that, right? So what do you think may happen is the data is directly moved from here to here, right? Most software developer believe that's what happens, but under the hood, that's not what happened because of cache. What really happens here is when you execute this instruction, the CPU will try to retrieve the data from cache directly, not from the DRAM. If the data is not in the cache, then it will retrieve the data from the main memory, then move to from memory to the cache, then move to the register. Okay, it's 2 steps. So let's say if we can accurately, doesn't have to be too accurate, just like the instruction set level with regular say functions with what the CPU provide. You measure the time before and after you load this. This is the instruction. Before the instruction, you get the current time. After the instruction, you also get the current time. Then you get the difference between them. Then you can tell a huge difference if the data is in the cache or if the data was not in the cache. Okay. So, well, first of all, that is intended effect, right? That's intended. That's what the cache thing is for, is to speed up this kind of thing. But because of this, we can say this is a CPU optimization. But because of the CPU optimization, it leaks some information attackers can use to guess what is accessed. For example, imagine there are several load instructions. There is a, let's say, then we can, if this one is small, then we know 3000 is recently accessed by someone, by some code, right? So in the last 15 years, I would say, in the last 15 years, people have been developing different attack strategies or attack primitives based on the simple phenomenon we just saw. Also, my team, we designed something before and we published in a good conference, and our attack can bypass the trust zone isolation of ARM device. So here I list 5 different primitives, and they all have quite catchy names: evict plus time, prime plus probe, flash plus flash. So those are just names, okay? When first time the people come up with evict plus time, then other people who come up with new approaches, they always try to find a catchy name. They do not imply there are only 2 steps or something, sometimes more steps. So we're going to talk about several, I think we're talking about 3 examples here, I guess. The first approach ever designed for this attack is this approach called evict plus time. It was published in 2005, so it's 16 years ago. So they used this approach, or they designed both evict time and the prime and probe. They used the approach to attack AES. The basic idea is to determine which specific cache set has been accessed by a victim program. Let me see if I will. Oh, I don't have an example of cache evict time. Okay, so this is a basic algorithm. Assume you are running multiple programs on the same operating system. This attack scenario can be extended to much more complicated cases. For example, you run different virtual machines on one Amazon cloud machine. You have several co-resident virtual machines on one Amazon physical machine. So those virtual machines belong to different people, but you can use this approach to attack each other. Okay. So here, let's think about a simpler model. We have one operating system. On the operating system, we have different programs running, and those different programs belong to different tenants, belong to different users, right? So let's say there is a victim, there is an attacker. The attacker can first measure the execution time of a victim program. Then you get a measurement. Then the attacker try to evict a specific cache set. After that, the attacker will measure the execution time of the victim program again. Those very 3 simple steps. Measure the execution time of the step 1, measure the execution time of vector program. You probably don't need anything special, right? You just need to get a time, that's it. Second step, evict a specific cache set. So how do you do that? Do you need anything special? How do you evict a specific cache set? What? Change the data? Good point. You cannot do that. There's no instruction for you to do that. No CPU offers that instruction. So what an attacker does is just to try to access the congruent addresses repeatedly. So the attacker will just use the load instruction to load data from some congruent addresses. What will happen is the value in its own memory address and those addresses will be brought into cache. And it will evict what is already in the cache set, right? But you can see this attack, everything is like a black box. You kind of know what you're doing, but there is no way for you to really debug to know that exactly happens, right? That's why you may want to do that many, many times. You access those different addresses many, many times, and to higher probability that you evict everything already in a cache set. Then after that, you're going to measure the victim program. So if the third step, the measurement is the results of the measurement is slower than the result of the first time, what does that mean? What? It's a miss. So what does a miss mean? So you're trying to infer whether the victim program used some specific memory address. So what a miss here means? Yes, they did use it, right? So they did use it. So the first time you do the measurement, it's fast because the content in the memory address already being brought into the cache. You evict it, you run the victim program again. The victim program has to access that data again, but this time the data is not in the cache. They have to get the data from the main memory, so it will be slower. Okay, so that is a basic idea of evict and time. Then there is another approach. It's called prime and probe. Quite similar. Let's say we have the attacker and the victim. They have their own address space. First, the attacker. So in this example, in this approach, the attacker runs first. The attacker will first try to occupy a set by just accessing congruent memory addresses. Try to fill the whole set. Then it will let the victim program run. If the victim program also access those congruent addresses, then some of the cache lines in the set will be replaced, or maybe all of the cache lines in the same set will be replaced, right? Then the third step, the attacker runs again. It will access those congruent address and measure its own time. If it's fast, it means its own data is still in the cache. The victim didn't replace that data. If it's slow, means the victim did replace that data. So it means the victim has been accessing some specific memory address. But this is, like I said, this is a side channel attack. There is no instruction for the attacker to directly say what is in the cache. They cannot. There's no instruction to do that. Okay. Any question there? What? The goal of the attack is not to slow down the program. It's trying to figure out what address the victim is accessing. That's a goal. Why is that important? I give you an example. In AES, how many of you took a crypto class before? Okay, so let's say we have an AES algorithm. The AES will encrypt your data based on your crypto key. So how is that done is giving your crypto key each beat, it will look up some tables and decide what calculations to be done. And that's a big table. The table has many items. Which item to use in that table depends on your key. So if the attacker knows what items in that table you are accessing, then I can somehow reverse engineer your key. That's the basic idea. It's not trying to slow you down, it's trying to figure out what memory address the victim is using. It cannot directly say what data is in the cache, but we can say what address is there. Flash reload is another attack. At the beginning, let's say if there is a memory block is cached, then the first step is the attacker will flush this memory block out of the cache. So here, well, you probably already identified the difference. The previous two approaches were still talking about cache set level. This attack is more fine-grained. It's at the cache line level. The reason we can do this is because there are instructions for us to directly evict cache line. So we first attacker will kick out this cache line. Then the victim runs again. So the victim may or may not access that block again. If they access, that block will be brought back into the cache, but not necessarily at that line anymore, right? It could be any line here. Then after that, the attacker will access that block again and measure if the victim just brought back the data. Okay. Okay, so next we are going to, well, we're going to say something more concrete, like all other attacks we have done. We're going to say something very concrete in our server. And then you can say exactly this approach actually works. So the code I'm using here, I take from a lab developed by a professor from Syracuse. It's called a Sidlab or Sidlab. Maybe it's Sidlab. You guys can check that later. He has all kinds of security labs from system software to network security. So what you study in this class, our software security labs are much more comprehensive than what he has. But he has network labs which we don't have on our server. So this is what I take from his website. Let's say this is a C code cache time.c. We have, first of all, we have a global variable array, and the array is 10. The size of the array is 10 pages. So in the system we're using, each page is 4 KB. So we're doing 10 times 4 KB. So that's a huge array. That's 40K. And that will be in the obviously main memory. It will be in the .data section, maybe .bss section. And we have the main function here. The main function, there's a local variable junk. We set it at 0. Then there are 2 local variables, time 1 and time 2. But those 2 local variables, we're not putting them on stack. We're actually directly putting them in registers because the value is sensitive. We directly put them in registers. Then there is a pointer to point to an address. There is a loop. So what we do at the beginning is we initialize this array. So there are 10 pages. So we are going to set the first byte of each page to 1. So we're trying to access it once, okay? So what will happen after this? So after this, technically, the first cache line in each page will be brought into cache, right? The reason we use 10 different pages is because they are not congruent addresses. They will go to different cache sets, okay? Now, after that, we will flush the array, flush all of those from the CPU cache. So in the Intel CPU, it offers instructions for us to flush the cache, but we cannot retrieve data from the cache. You cannot read that. You can only tell it, I'm going to flush the cache line which belongs to this memory address, but you cannot retrieve that. There's no instruction to do that. Okay, so now we flush it. So we flush everything. So technically, so now should be pretty sure that nothing is in the cache. Those 10 cache lines, those 10 addresses, none of them in the cache, right? Okay. Now let's do something really interesting. We're going to access those two items. One is at page 2, another is at page 8. We're going to access them. We're going to set the value. So what will happen? So those two lines will be brought into the cache, right? Okay, so that's what is going on here. Then we're going to measure how long does it take to access those 10 different items. There are 10 items. Technically, 2 should be in the cache line. In the cache, the other 8 probably will not. So we're going to access that. So the instruction we try to access for command or statement here is only this one. We're moving the address down to the jump. Okay, we don't care about the value, we just try to access that. Before that, we use this function to measure current line. After that, we measure. Okay, that's it. So let's run this on the server. I think the server code could be a little bit different. Let's do the cache time. So this program doesn't, by the way, this program doesn't have to be set UID program. It's just because the way we design the server, everything we put here will be a set UID program. And later we're going to show you this program doesn't have to be a set UID program. It's just a regular program. So let me, you can see this is almost the same source code, it's just here. Here we're using accessing 3 and 7, different from my code on my slides, which is 2 and 8. Here we're doing 3 and 7. Okay. So after we compile this, we simply run this program, and you can see. So the first one, 450 cycles. The second one, 500. Let's say the zeros, 400. First, 500. Second, 500. Third one, we get access, 400. Okay. It's not really much smaller, right? You can go those because it's 7 much smaller. Okay. So this is a lot of randomness there. Okay. So you probably want to do this experiment many times and get the average. If we do this again, oh, this time things are much different. The third one is 142 cycles. The seventh one is also 142 cycles. The others are much higher. It's not that deterministic, but still quite consistent. Okay, so run this again. So this one, 1, 1, 8, 1, so let's compile this program again. I think I have a command here for you to compile this program. When you compile this program, you need to use the native command option. So the architecture, you need to choose native. So it makes sure that it actually runs on your CPU. Let's say So we don't have access here, so we need to copy that to cache time. Let's copy to 10. And let's go to 10. We're going to compare this. So we got it, a.alt. This is not a SetUID program. Hold on, let's change the numbers a little bit. Okay, so we just tried the 3, 7, right? Let's try 2, 5, maybe another one, 3, maybe 8. Okay, the value we assign to it doesn't really matter, but just trying to access that. Compare it again. Why there's a warning? Oh, okay. Doesn't matter. Let's run this program again. Which one is supposed to be smaller? 258, right? I think it's 258. What do we have here is 258. We run it again. Let's say when the 2 is smaller, 5 is smaller, 8 is also smaller. Okay? So it's quite consistent. It's quite consistent. This one, this one, this one. They are smaller than others. Do it again. Oh, this one is still small. Okay, this one is a little bit bigger, but still smaller than others. See, you see, it actually works. Okay. So that is the cache time, the simple program to measure the time. The next, let's say, the flash reload example, which we also put on the server. Flash reload. This program is a little bit more complicated, so let's walk it through. First, we have a global variable, which is 256 pages. We have a global variable temp, and we have 1 byte of secret. We call it, the secret is 94. We can change it later. So this is our secret. Then there is a cache hit threshold we need to set. Depends on what we saw just now. It's probably will be 200 something is reasonable. How many CPU cycles, right? So a cache hit is probably lower than 240, 250, I would say. Then the delta is just 1K. So let's say the main function here is, the goal here is we're going to use the cache as a side channel to transmit a secret. We're not directly giving the secret through a global variable, but we're going to use cache as the side channel to transmit that. So we're going to first flash the side channel, then run the victim program, then reload the channel. The victim program is, I think we're not transmitting, we're stealing things from the victim in this case. Let's say how flash works. So the flash is, we're going to flash we're going to flash the value from the cache. Okay, so here we initialize things. Then we do this, use the library function, memory management, flash, to flash all the items from the cache. So none of them is in the cache. This eventually maps to CRF flash instruction. I think we can show here. Do a obj dump. We look for the flash function. So this is a flash function, and you can see here we have this instruction, CL flash. That is actually an instruction offered by Intel to flash data out of the cache. Okay, and at the C code level, this function is eventually will be compiled into that instruction. So this is a flash. After flash, we run the victim program. Let's assume a victim program. The victim program is trying to access some memory location. And we are trying to figure out what it is trying to access. The victim program is going to access, there are 256 items there, right? They're trying to access the secret one, which is 64 in our case. That's it. The victim just do that access, nothing else. Just moving that data from one global, from memory to another global variable. By doing that, the CPU needs to access that. We can do that again. You can say this is a victim. So some of the instructions, one of those moving instructions is actually moving the data from the memory to register to do that. Then after that, this is the reload part, which the attacker try to guess what is the secret. From here, you can see this piece of code. This piece of code didn't use the global variable secret, right? Didn't use that. We're not directly reading that. We're just trying to use cache to guess what that is. Very similar to the coding for before. The only difference here is we print out based on the cache threshold. If the cycle is very small, the secret. So if we run this program, okay, you guys already saw that. Right now in the source code, we set a threshold of 80. On the same machine, the cache we just did is like the secure cycle is like 20,000. So 80 is not going to match anything. Nothing will be a small update. So we probably will not get anything here. See? We do not get anything. But if we let's compile this again. Oh, we need to change that. Let's set the threshold like 240. If we set it too high, it will believe there are too many secrets, right? Let's set 240, probably reasonable. Then we compile it again. Good. Then we do a out. Yeah, we got it. See? Let's change the code again. Oops. Let's change this to 194, 132, whatever. And compare this again. Why there is a segment fault? What did I do? Char. What? Charge to. Interesting. No. Okay, see, we changed to 56. You can still get it. of course, just for the attack to be successful, you need to somehow know the right threshold. If you set the threshold very big, like 400, then probably we are getting several of those, right? See? So in this case, all those items we came back very fast. So the program is also actually not. But if you run that many times, okay, this time only 2. Do it again, this time also 2. No, always 2. Yeah, this time is only once, right? So this is not a deterministic, not always deterministic, but at a high level, I believe you'll say this is possible. Okay. Okay. Any questions? That's the easy part. Hungry address. So let's say you're trying to attack again. First of all, like over a share line, then you can know that that number. Okay, one more slide for today. So as part of your homework today, you are going to figure out on the server and also on your own computer what CPU you are using, cache configurations. And some of them already have different hardware protections already to defeat the attacks we are. You can use the ls CPU command. Say we do an ls CPU command. You can say the server we are using is a x86 CPU. The address is actually, so the 64-bit CPU, the address space is not really 64 bits, it's 57. We're not using all of them. Then how many CPUs we have on this one? We have 32 CPUs. Give you those information, and also let's say, so L1 cache, L1D, L1 data cache, 1.5 megabytes. L1 I cache, 1 megabyte. L2 cache, 40 megabytes. See? Ooh. See? Well, the server I bought is quite small. I something like and I think we're not showing all the CPUs. We're only showing the CPUs for the search machine for that server. I think the CPU we have 196 CPUs, I believe. But you can see the cache is huge. The L3 cache is 1.3 gigabytes. That's huge. Yeah. This is CPU cache. This is not a file or something. Yeah, that's huge. Then you can say, so next week we're going to talk about those attacks, Meltdown and Spectral. And you can see that this I bought this last fall, I believe. So you can see the CPU already have some kind of mitigations to those attacks. Those attacks was introduced like 3-4 years ago, Meltdown and Spectral. We're going to talk about them next week. So you can do the same thing on your local CPU to find out what what the CPUs you are using. So see, so for my local CPU, the L3 cache is only 8 megabytes. Okay. So I need you to, in the homework, I need you to go deeper. You need to get the model name. You need to Google it. Because you can see here, it doesn't tell you how many weights your cache is. Right? That's a very important information. That's actually a 4-way cache. So I need you to Google this to figure out more detailed setting of your CPU. Let's say, where can we find out cache information? Maybe here. Some website will tell you everything. Anyway, you probably need to do a lot of search with the website. Some of the websites will give you more information each layer of a cache size and for each of them, how many weights are there, or further divided into smaller cache chunks. I saw that before, but I'm not sure which website gives those kind of information. Oh, here, see? This website, cpu-word.com, it actually tells me my CPU, the L1 cache is the instruction cache and data cache are separate. The instruction cache is 4 times 32 kilobytes, and the 4-way, it's 8-way associated cache. The data cache is 12-way. The L3 cache is actually even 6-way, 8 megabytes. There's one price of these 4 different is actually divided into 4 caches. So there are 4 L3 cache. Each of them is 500 kilobytes and 8 megabytes. So those are the information you need to do. So those are the information you want to find out for your own CPU. Okay, any other questions? Yeah. Yes, because most of the cases you do SLR, you are recognizing the Okay, if no other questions, see you guys next week. So I will post the homework later today, but because this week we didn't have the class on Monday, I will cut you some slack here. So the homework due for this one will not be Wednesday next week. We will use, let's say, Friday next week. Well, see you guys next week.